Good morning, students. In previous lecture, we discussed about ideal gas laws and ideal gas equation, and the gases which follow all those laws and that equation for the entire range of temperature and pressure are called ideal gases. But in actual practice, there is no ideal gas. The gases behave ideally for a certain range of temperature and pressure, and such gases are called real gases. Let us see what is the behavior of a real gas. So firstly, we'll discuss what are the ideal gases. Ideal gases are the gases that follow all gas laws and satisfy PV is equal to nRT equation for the entire range of temperature and pressure. And this ideal behavior is derived from kinetic molecular theory of gases. Actually this theory is based on certain assumptions. As you can see in this diagram, gas molecules are in constant motion with high speed, or you can say even during their movements they collide with each other, and these collisions were considered as elastic collisions, and there is a lot of space present between the particles compared to the size of the particles itself. So these are the main assumptions on which kinetic molecular theory is derived. Let us discuss few postulates of kinetic molecular theory. Gas is a collection of a large number of atoms or molecules, and these are very small in size, like a point mass. And particles are generally far apart in such a way that their interparticle distance is much larger than their individual size, and a large free unoccupied space is present in the container. And as compared to the volume of the container, the volume of the particle is negligible. And particles do not have any attractive or repulsive interactions among them. Means particles in a gas, as they are far apart from each other, so they do not experience any attractive or repulsive forces. And the particles are always in constant motion. And because of lack of interactions and a large free space available, particles randomly move in all directions but in a straight line. Next postulates, because of motion, gas particles occupy the total volume of the container. Means jitna volume container ka hai, that whole volume is occupied by the gases because of their random fast motion. And the volume of the container is treated as the volume of the gases which are filled in that. Since the particles are always in motion with different velocity, they have different kinetic energy, and the kinetic energy of the gas is actually the average kinetic energy of all the particles present in that, and this average kinetic energy of a gas is directly proportional to the temperature in Kelvin scale. And as we know that particles keep on moving, and during this movement they collide with each other as well as to the walls of the container. But these collisions are perfectly elastic. Means particles do not change the energy or momentum during these collisions. Collisions of the particles on the walls of the container exerts a force on the walls of the container, which is known as pressure exerted by the gases. And number of collisions increases with increase in temperature. Hence, the pressure exerted by the gases are also increase with increase in temperature. Let us see few characteristic properties of an ideal gas. Gases that follow all gas laws are said to be ideal gases, and they follow these laws for the entire range of temperature and pressure. Gases whose behavior can be predicted by kinetic molecular theory are called ideal or perfect gases. But in real practice, no gases are truly ideal, because no gas totally obeys all these gas laws. For there are certain range of temperature and pressure at which they behave ideally. An ideal gas is an imaginary gas that is perfect and does not follow everything perfectly. An ideal gas does not condense to a liquid at low temperatures. An ideal gas does not have forces of attraction or repulsion between the particles. An ideal gas is composed of the particles that have negligible volume as compared to the total volume of the gas. So these are certain behavioral aspects of an ideal gas which are otherwise absent in a real gas. The real gases are the gases which do not follow all the gas laws for the entire range of temperature and pressure. A real gas behaves ideally only at a low pressure and a high temperature, because at low pressure or high temperature the volume is very large, and in that case the particles can behave in ideal manner. And the gases that act most like ideal gases are few only, which are the lighter gases, hydrogen and helium gases. Now we'll discuss deviation from ideal behavior. Real gases deviate from this behavior, ideal behavior, at a high pressure and low temperature. As you can see in the graph, gases like hydrogen and helium, their curve is lying above the curve of ideal gas. PV versus P curve for an ideal gas is a straight line parallel to x-axis. But as you can see here, all these real gases do not have such kind of graph. Rather, either these graphs are lying above the ideal gas curve or somewhere it is below. So in this way they are gases, and as you can see that approximately low temperature, when temperature is quite close, when temperature is high and pressure is low, in that case you can see that the plot is quite resembling to the ideal gas curve. But as soon as we increase the pressure, the curve becomes deviating from the ideal behavior. So let us discuss now what is the cause of such deviation. Actually, kinetic molecular theory has two faulty assumptions. First one, that interparticle forces are negligible in gases, and secondly, particles have negligible volume as compared to the total volume of the gas. But these two assumptions become wrong when we discuss the behavior of a gas under high pressure or low temperature. In that case, the volume becomes less, and in lesser volume, intermolecular forces of attraction become significant, and individual molecular volume is also significant. Now, Wonderwall studied the behavior of real gases, and he assumed that the particles in a real gas have a definite volume and hence cannot be compressed beyond a limit, and two particles at close range interact and have an exclusive spherical volume around them. So on the basis of these assumptions, Wonderwall successfully derived a state of equation for real gas, and by doing certain corrections in pressure and volume terms. Firstly, we'll discuss pressure correction. The particles on the surface and near the walls of the container do not have particles above the surface and on the walls. Okay, means the particles जो walls के आसपास हैं या surface पे हैं, उनके बाहर की तरफ कोई particles नहीं है, but they are getting attracted by the particles which are present inside the gas. Hence, there will be net interactions or pulling of the bulk molecules towards the bulk, that is away from the walls and the surface. And the molecules experience a net interaction away from the walls. और इस तरह से वो जब collide करेंगे walls के साथ तो उतना pressure नहीं डाल पाएंगे जितना ideal case में होना चाहिए था. तो hence in real gases the particles exhibit lower pressure than shown by ideal gases. Wonderwall corrected this pressure term by adding certain numerical values, and hence the pressure of real gas when it behaves ideally must be equal to the observed pressure, which is lesser actually, due to interactions plus this corrected term. So this is equal to P observed plus A n square over V square. Here A is Wonderwall constant, which is a measure of intermolecular forces of attraction, n number of moles of gas, V is the volume of the gas. Secondly, Wonderwall also added one more correction in the volume term. As kinetic molecular theory assumed that particles, individual volume of particles is not significant when it is compared with the large volume of container, but at high pressure this volume may be significant, and for a real gas this volume needs to be subtracted from the volume of the container. Hence, the volume of real gases when they behave ideally is equal to V minus NB. Here V is the volume of the container or the ideal gas minus correction factor NB. N is the number of moles of gas and B is a Wonderwall constant, which is measure of effective molecular size or volume. Now if we put the values of both corrected pressure and corrected volume in normal ideal gas equation, we'll get this equation which is used to define or to discuss the behavior of a real gas in terms of A and B. This equation is actually given by Wonderwall and it is known as Wonderwall equation, or this is also called as equation of state for a real gas. Here A and B are Wonderwall constants and rest P is pressure, N number of moles, V volume, R gas constant, T is the temperature in Kelvin. And units of A and B, you can also see A is equal to, the unit of A is atmosphere, liter square, mole inverse square, and unit of B is liter per mole. Next very important term, compressibility factor. It's represented by Z and it is a measure of deviation of a real gas from ideal behavior. Means Z से हम मेजर कर सकते हैं कि एक गैस जो एक रियल गैस है डेली प्रैक्टिस में, रियल लाइफ में, वो आइडियल बिहेवियर जो एक हाइपोथेटिकल फिनोमिना है उससे कितना डेविएट होता है. एंड फॉर दैट वी कैन plot a curve between the value of Z. Z is actually ratio of product of P and V to product of nRT. If we plot a curve between Z and pressure, so it will be a straight line for ideal gas because ideal gases have this ratio of PV over nRT equals to 1. So ideal gases will show a straight line parallel to x-axis, whereas you can see that for real gases this curve is not lying along with the ideal gas curve. Rather, somewhere it is showing positive deviation in case of hydrogen and helium, whereas somewhere it is showing negative deviation for carbon dioxide, methane, etc. And for these gases, Z is initially negative, but after a certain range of pressure, it becomes, at very high pressure, it becomes greater than 1. The significance of compressibility factor Z is that actually Z can also be represented by the ratio of actual or observed volume of a real gas to the volume when it is considered to behave ideally. So that is Z is equal to V real over V ideal. If Z is equal to 1, the gas will behave ideally. If Z is less than 1, then the gas is less compressible as compared to the volume which is considered for that particular gas. And if Z is greater than 1, then the gas is more compressible than the expected ideal behavior. So in this way we can find by determining the value of Z. Next is Boyle's temperature. Actually, gases deviate from ideal behavior for a particular range of temperature and pressure. And if we plot a curve between the value of Z and pressure for different temperatures, we can observe that with increase in temperature, this curve or the minima of the curve is decreased. Means the gases start behaving more and more ideally at high temperatures. So there is always such temperature value where a real gas behave ideally for an appreciable range of pressure, and this temperature is known as Boyle's temperature. Means इस temperature पे gases ideal behavior show करेंगी एक large pressure range के लिए. In this curve, the gas is behaving like almost like an ideal gas at this temperature region of T2. Next very important property is the critical point for a particular gas. Gases, as we know that on cooling, they condense to form liquid, and there is actually a critical point in the end point or you can say in the equilibrium of gas liquid vapor of equilibrium or gas liquid equilibrium, and this point is actually the end point of any equilibrium curve. Here in this graph, as you can see that at this critical point, the howsoever pressure if we apply on a gas, it will not be converted into a liquid form, because under this critical point both liquid and vapor coexist, and at high temperatures the gas cannot be liquefied by pressure alone after this critical point. And at this critical point the temperature is defined as critical temperature Tc, and the pressure at this particular temperature is defined as Pc, and the volume of the gas at this particular point is called as critical volume. So these are critical points for a particular gas above which the gases cannot be liquefied. So critical temperature can be defined as the maximum temperature above which a gas cannot be liquefied howsoever high pressure may be applied. In the curve you can see the pressure volume curve of CO2 gas, and as you can see for temperature 13.1 degrees Celsius there is a straight line representing phase transfer from gas to liquid for carbon dioxide gas. At somewhat higher temperature you can see 21.5 degrees Celsius. There is also phase transfer you can see from gas to liquid, but at a temperature 13.98 degrees Celsius there is the last point, that critical point is observed, beyond which you cannot find that phase transfer. Means above this temperature carbon dioxide gas cannot be converted into liquid form by applying a large amount of pressure. So this 30.98 degrees Celsius is the critical temperature for carbon dioxide gas. In this way, each and every gas has a particular temperature above which it cannot be liquefied जितना भी उसके ऊपर हम pressure लगा दें. And this is a important characteristic property of a gas which is a measure of in intermolecular forces of attraction as well. Higher the critical temperature, easier is the liquefaction of gas, because critical temperature measures the intermolecular forces of attraction. If the gas will have higher intermolecular forces of attraction, it can be liquefied easily by applying pressure at room temperature as well. And the table showing various critical temperature and pressure and volume values for various gases, and here you can see helium is the gas having critical temperature 5.2 Kelvin. So this is very low, and that is the reason all those gases which have critical temperature very low from the room temperature, they cannot be liquefied at room temperature. And initially these gases were considered as permanent gases, but now we can liquefy them by applying high pressure after cooling below this critical temperature. And in this table you can see carbon dioxide gas, ammonia, water and HCl are such gases which have critical temperature above room temperature. Hence, they can be liquefied easily at room temperature by applying pressure. I hope the things are clear to you all. Thank you and have a nice day.